Hello everyone, I'm going to be talking about how to make a 4-bit counter using JK flip-flops. So what we're looking at here is a state table. We're starting at all zeros here. And what we have here is the next state. So we see that it goes from 0 to 1 on this side. Let me just to be clear. State table. And if you look at what we're counting, we're basically counting from 0 all the way down to 15 here. This is 15. And at the same time, we're also letting the system know that, so for instance, if we're in 1 0 0 0 here, we know that the next state has to be 1 0 0 1 right here. So that's what this star means. This is basically next state. So I can select this here. Current state. So out of this, we have to make K-maps or Carnot maps. Well, before we do that though, it's one thing to note is that this is a 4-bit counter. So we're counting from 0 to 15. Or in HEX, if we're considering the HEX equivalent, we're counting from 0 to F, because it goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's counting in HEX. Okay, so before we continue, I'm going to assume that you know what a logic gate is, what an AND gate is, what an OR gate does. There are plenty of tutorials on YouTube that explain that, so I figured I should skip that. This should primarily help the engineering students trying to figure out how to design a counter from scratch using JK flip-flops. And this is basically how you do it. But I guess to summarize, I'm going to assume you know that if I say J equals to AB, that's simply an AND gate like this, where the inputs are here, output is here. Let's say if I say J is equal to A plus B, I'm going to assume you know that that's already an OR gate. Like that. And a NOT gate, so let's say B NOT, that's simply gonna look something like this. So like that, and then output we get B NOT. So that's a simple NOT gate. Here we now know we have the foundation of our design. So I have the K-maps here. They're already completed for us, but I'm going to show you how to get to them. So it's important that we label our K-maps like this. So 0 0 and 0 1 1 1 1 0, and the same thing for this side. Notice the 1 1 here. That's simply how K-maps work. If you want a more in-depth explanation as to why that is, you'll have to read a logic design book. So let's look at D here, D next state. We see that these are all zeros here. All of the next states for D is all 0 here. and then it becomes 1 right here. So let's see what this 1 corresponds to. It corresponds to 0, 1, 1, 1. So AB has to be 1, 1 right there. C and D has to be, or DC rather, we can consider it as a pair, has to be 0, 1. So we look at this pair, and then we look at the one that says 0, 1. There it is, and that's the one. So let me get rid of these marks. So that's where this one comes from. And then you continue. So I guess I should circle it to make sure that's where that one comes from. And then you continue here on this, on the next one. We see that D is 1, but the rest is 0. So we're looking at 1, 0, and then 0, 0. So look at these two pairs, it's 1, 0, and then these two pairs. For this given one, it's basically 1, 0, 0, 0. So we look at the pairs here. 1, 0. No, sorry. It's 1, 0, of course. DC is the first one. And then 0, 0. Right here. So that's where this one comes from here. And for completeness, I guess I can go through all of them. So the next one is 1, 0, 0, 1. So 1, 0, once again, 0, 1, there it is. 1, 0, 1, 0, so 1, 0 again, and then 1, 0 here, there it is. Now we have 1, 0, 1, 1, which is this one. So 1, 0, 1, 1, so that's 1, 0, and that's 1, 1 right there. Next we have 1, 1, 0, 0. So 1, 1 is here, 0, 0 here, there it is. Let's continue. We have 1, 1, 0, 1. So 1, 1, 0, 1, there it is. Last but not least, we have 1, 0 and 1, 1. Hold up. BA. So yeah, okay, 1, 0. So I got confused. And then 1, 1. So 1, 0, 1, 1, and there it is. And there's all of the whole K-map. So you want to do the same thing for all of the letters here for D, C, B, and A. So at this point, we're now ready to continue to writing our equations. Now, as these K-maps stand, we can actually write some equations for D flip-flops. So we can say something like this. D, well, first we have to make some circles here. Let's call it DD. So let's make a circle here, circle here, circle here, and a circle here. So what we'll have is something like this. DC naught plus, let's add this one here while we're at it. So this is gonna be, let's go in order. D naught C BA plus, let's do this one now. What is that? That is DC and B naught, because we have a 0 here and a 0 here. And then we want to do the last one, but we don't want to use it by itself because that'll just make the circuit more complicated. So what we do is we take that one and this one, combine it into one. So what we have is now BC times, what's the one they have in common? They have in common the A naught. So this is how you write the equation for this. And I'm assuming that you can interpret what I just did here and extract the same equation for the other cardinal maps. Now the reason you want big circles is because, like this one, is because the bigger the circle, the less components you'll require, I suppose you can say. So what all of these ones have in common here is that it's simply a 1 0, so it's just the D and the C naught. So that's where this comes from. But what you'll notice here is that this is a long equation, and we're going to have 4 of these things. So that's, I'm going to have a 2, this is a 2 input AND gate, and then I'm going to have to accommodate for this knot here. And then we have a 4 input AND gate, accommodate for that knot D, 3 input AND gate, 3 input AND gate, and it's just kind of gets complicated. So what we'll do is we'll do the shortcut method by using JK flip-flops. And this is why JK flip-flops are so great. It greatly simplifies when you're designing these counters, and I guess design in general. So when you're looking at this, we want to start with JD. This is going to be the J part of our JK flip-flop for this bit, because at the end of the day these are all one bit. All of these K maps are representative of a bit that we're counting. Okay, so I went ahead and I copied some K maps that I used before, these ones right here. I'm going to be reusing them when I make my JK equations. So we're going to start with this K map here. So JD, right? This is the expression that I want to find. What is JD for this flip-flop? And you'll see that I have the subscript D. That's basically making reference to the J portion of the flip-flop of the D, not to be confused with D flip-flops, but this is the J portion of this particular flip-flop, and each one of these is going to have its own flip-flop, in fact. So what we do now is the following. I'm going to go ahead and copy this one, copy this K map here, copy, paste, and then I'm going to label it. And I'm looking at the D, so just make sure that we're clear that this is the D. So then we say C, and then we say BA. So what you'll notice is that I'm only looking at the portion of the K map where D is equal to 0. So I'm basically only looking at this portion of the K map, because that's how the design with JK flip-flops work. And that'll give me the J equation. So I copy that over and then I put a 1 here. And again, this is only this portion. So now I can make my circles. I'm going to go ahead and circle that, and then write my equation. And then we see that we have A, B, and C. So we have A, B, and C right there. So now we have to look at the same, so for K that is, we have to look at the same kernel map, but now we're only looking at the case when the D is 1. So let's go ahead and copy the K map here. Put it right here. And then I want to add the labels once again. But here's an important key, is that I have to be consistent with my labeling. So if I'm only looking at this portion of the K map, the C on this side is starting at 1 and it's ending at 0, so I have to change these two. Call it 1, 0. And then I copy the rest. So this K map that I just did here, I'm missing the A. So this K map represents K not D. Right? But I don't want K not D. K not D will give me something like with like 3 expressions, and I don't want that. So what I want, I'm just going to leave a couple of dots here. What I want is KD. So to get KD, all I have to do is just invert the whole K map. So if it's a 0, it becomes a 1, and if it's a 1, it becomes a 0. So you can already imagine what this would look like if I did that. So imagine that this here, it becomes a 1. Alright, so all you have to do now is just circle the empty space. And what we see is that we have ABC again, right? We have a 1 on the C and then the 1, 1 on the BA. So that's just all 1s for the signals here. So KD equals to ABC. Okay. And we're going to move on to now the next kernel map. Let's look at C. So now I'm going to be focusing my attention on this one. Paste. So I'll do one more and then I'm going to skip the other two. Actually, I might do this one here because the K maps are of like a different shape. So I'll do 2 more. So here we have so now we're looking at C. So now we don't include it in our K and J kernel maps. And then we can say, okay, J, C. So we're looking at the case where C is equal to 0. So we see that C is 0 here and C is 0 here, and then we copy that over. So we look at this here and we look at this one here. We copy that over here. 1, 1. We make the circle. What does that give me? BA. Because we have the 1, 1 here. Doesn't matter whether D is 0 or 1. The signal is BA. So now, let's erase my markings. Let's paste another K map right here. This is D, this is BA once again, and then this is KC not. And then I'm looking at the case where C is 1, 1, 1. There it is, 1, 1, 1, 1. Nothing here, and 1, 1. But as you know, I don't want this expression here. I want something simpler. So what I'm doing is I'm just going to call it KC. And that means that all of these get inverted, as you know. So then I circle here. And then I get BA. and obviously this is for C. Okay, let's do B. I'm gonna skip A, but you'll see what happens when I do B. So that's why I have this other shape, this other K-map shape here. Copy that. Oops. Why is it not copying? Try it again. So now we're looking at B. So let's put it here, down here, so that I have space for my equations. So I have DC up here, and I have A here. So, and this is the one I'm focusing on. So now I look at the case where, where B is equal to 0. So I see that B is 0 right here on this one and this one. So this here. So A is going to be 0, 1. So I have to make sure that my A is in this order, in 0, 1 order that you see there. It's already there, just like that. So all I have to do now is just copy what I see there. So that's 1, 1, 1, 1. So now, J, B. What is that? Well, make my circle. A, straight up. I move on. What do we got here? We got DC, and we got A. K not B. I want to look at the cases where B is equal to 1 on this K map here. So B is equal to 1 here and here. But notice that my A is 1 here and it's 0 here. So I have to change that. 1 here, 0 here. And then, so now it's good. So now I just copy it over. 1, 1, 1, 1. Sorry, that's wrong. Copy it over. Yeah, there was no need to do this. I can just call this 0, 1. And then the ones, the point is you have to be consistent with how you do it, because this can be a little tricky. Okay, so if I just call it 0, 1, the ones is located when the A is 0. So I just put it up here. Yeah. Well, the way I had it before actually should be fine also, actually. So let's look at that. So it's, if I say 1, 0, that's gonna be 1, 1, 1, 1. Yeah. So this gives me K naught, but I don't want K naught. I want K, B. So basically I'm just gonna circle this one here, and I get A as well. So notice here, you do it either way, it works, and it should. And something that you'll notice by now is that the J's and the K's here are the same. And that's for completeness sake. This is the one I circled because I don't want the not K, I want the K by itself. So I have to circle the empty space. But anyways, this J and this K, they're equal in all of these cases, even the last one. It's not always like this. For this particular counter, it just so happens to be like that. Okay, before going to multisim, I want to show you guys the flexibility that these state tables have. Basically, you can choose any output you want, or any next state that you want. So let's say that rather than have this D here, I'm gonna call this an input, and let's say D is activated, or if D is logical 1, let's say that I want to count down rather than counting up. So how do I do this? I would have to split this into 2. So if I'm going to be counting up, I can count up only up to right here. So let me just go ahead and write out the 3-bit counter. So depending on the state of D here, I can say, okay, let me count up or let me count down. If D is 0, let me count up. If D is 1, let me count down. So I'm going to go ahead and show how you would set that up with the state table. But first I have to draw or write these binary numbers. Okay, so let's say that D is 0, and then we see that we're counting all the way up to 7 basically. So we're starting at 1 here, and then we're counting all the way up until 7 here, and then it restarts when it reaches the next state right there. So then it'll repeat. But let's say that D is equal to 1. What I want this to do is I want it to count down rather than up. So how would that look like? So let me just, and by the way, this section here is no longer relevant, so we can sort of cross that out. So let's say that, and then I have to cross all of these out also. So let's say that D is toggled to 1 right there. So what should I do here? I'm going to say that where the next state is going to be 1. And you'll see why in a moment here. So that'll bring me down here. This will bring me down here. So now I'm here. And what do I want the next state to be if I'm here? So let's look at this side here. Counting here like this from 0 to 7, that's counting up, but I want to count down, so I want to basically go up here like that. So then what I'm going to do is I'm going to say, okay, this is going to be 1, 1, 0. So then my current state now becomes this one, like that. So I'm going from here, oh, that's the wrong one. I'm going from here to here, and then I want to keep going like this, so on and so forth. So what does that look like? So now my current state is 1, 1, 1, 0. My next state is going to be, that's right, 1, 0, 1, because I'm counting up. So then current state becomes this one here, 1, 1, 0, 1. So my next state is going to be 1, 0, 0. So then this becomes my current state. So then I adjust this one here like that. What do I want my next state to be? 0, 1, 1. And so on and so forth. You can already sort of see how it works. It's going to be 0, 1, 0. And then it's going to be 0, 0, 1. And then last but not least, you're going to have a 0, 0, 0 like that. And so what you have here is, given that D is turned on, you're going to be counting down. So and this works. If you guys would like to see me design this one instead, or rather for the next video, I can do so. Just leave a comment requesting to do so. But for now, I'm going to go back to the hexadecimal counter from 0 to F. Okay, so as an exercise, I want you to write out the K maps that correspond to this K map here and find the JK equations. If you do it properly, what you'll see is you'll have J of A is equal to 1 and K of A equal to 1. So what does it mean when you have a 1? Well, that simply means that your entire K map is just going to be filled with 1s like this. So this is what you should expect to see when you write out your K maps, but I want you to do it. I want you to prove it to yourself. So for now, we have our equations all laid out. Let's rewrite them down here. So J A equal to 1. Well, it's equal to Ka, and that's equal to 1. JB equal to KB, and that's equal to A. JC equal to KC, and that's equal to BA. And then JD equal to KD, and that's equal to ABC. Or I guess you'd call it CBA, just to be interesting. So we now have all of our equations necessary to build a counter. What this tells you here is that you're going to need 4 flip-flops, and each of the flip-flop is going to be hooked up. So if you look at flip-flop for integer D, the J and the K of it are going to depend on C, B, and A. And C and these letters are considered as the output of the JK flip-flop. So I'm going to show you now. I'm going to show you that now in multisim. Okay, so here we are now in multisim. I hooked up the JK flip-flops to the power and to the clock, but I haven't hooked up the logic just yet. So let's just go over what I did here. So here's my VCC. I'm powering each of the flip-flops right here, and on the bottom as well. I have the clock coming in here on the underneath. It's being placed into the center of each of these flip-flops. You can see that here is the J and here is the K of the flip-flop. And with this side here on the right, this is just the output, and the one underneath it is just the NOT of that, so the inverted version of the output. Okay, and then I have my logic gates here ready for when I'm going to hook them up. And let's see, what else do I have here? I also have the decoder from binary to hex hooked up. So you'll see that this leftmost flip-flop is the least significant bit, so we can call it A, and then so on and so forth. This is B, C, and D. So that's how I have them hooked up. So this one here, least significant, followed by this one, and then followed by the most significant. Okay, so let's look at our equations that we have here. This is what I wrote out earlier. So I want my JA and my KA to be 1. So that means it's going to be on at any given moment. So I'm just going to go ahead and hook them up like this. And this is the important part when you're designing these counters, is, you know, hooking them up according to the equations that you got. So now I'm moving on to B here. So B is going to be just A. So JK, and let's place a wire. Place wire right there. So what I have here is simply JB and JK is equal to A on this second flip-flop. It's just a straight connection. Now let's move on here. So now I'm moving on to the C flip-flop. This is the C flip-flop, and you can obviously label these to make it clearer for yourself, but I'm not going to do so. So let's see what we have here. B and A. So I want B to go into the AND gate, and I want A to go into that same AND gate. So let's hook that up. That is my A. That is the B. And that is going to go into my C flip-flop. So let's put it into the K first. Doesn't matter which one you go first, obviously. And there it is. So you move on. Now it's telling me that I need to hook up the D flip-flop. I need to hook it up with, you can interpret this as a 3-input AND gate. Or what you can do is you can get the output from the previous one and then treat it as a 2-input AND gate. So you can treat the C combined with the output of the B and the A and treat it, and then put it into the second AND gate, and you're not going to have a need for a 3-input AND gate. So this will save some time and, more importantly, logic gates. So let's go ahead and do that. So in here I'm going to have B and A, and then in here is going to be the C. Yeah, so that's C, B, and A. And then I'm going to be outputting it into this K here and the J right there. Okay, and that should complete the circuit. That is the most important part when you're making these counters. So let's run it. Let's see what we get. Starts at F 0, 5, 6, 8, A, B, C, D, E, F. There it is. Okay, so this practically concludes this video. One thing I'd like to mention though is this component converts the binary values into hexadecimal values, or into a format that is easily readable by humans. So it takes these 4 wires, and you'll see here I have a bar, an LED bar. This is binary. This is an easy way of looking at the counting in binary. But yeah, back to this component here. This has a decoder inside of it, and it decodes all of the binary values and turns it into hexadecimal. If you guys would like to see me design one of these decoders, I can do so. All you have to do is just leave a comment down below, asking for it, and if enough people ask for it, I can do it. I can also do, rather than counting up, I can count down, even though it's practically the same, but if enough people ask for it, I can show how to do it and show every step of the way. But yeah, that pretty much wraps things up, and thank you for watching.